Hello students, so in the previous class we started with Bessel's function, and as I mentioned in the previous class that we will cover only two special functions, right, Bessel's and Legendre polynomial. So today I am going to talk about Legendre polynomial and Legendre differential equation and some properties, if time permits, associated with it. Right, so let us start. So first of all, so this problem, or sorry, this equation, so the Legendre polynomial, so Legendre equation and polynomial right. So this equation arises, I mean it has some application, arises in problems with spherical symmetry, symmetry in mathematical physics, So how does the standard form look like? So the standard form of Legendre's equation of degree n is given by 1 minus x square d square y by dx square minus of 2x dy dx. So it is better to use one uniform notation, 2x dy dx, that means y dash plus n into n plus 1 into y equals to 0. This is equation number 1. So clearly here the origin is an ordinary point. X equals to plus minus 1 is the singular point, but the origin is an ordinary point, of equation 1, right. So we can write down the solution as therefore the general solution is given by yx equals to ay1 plus by2, where a and b are constants, and y1x equals to 1 minus n plus 1 by factorial to x square plus n minus 2 n plus 1 n plus 3 by factorial for x to the power 4 minus dot dot and so on. y2x will be x minus n minus 1 n plus 2 by factorial 3 x cube plus n minus 3 n minus 1 n plus 2 n plus 4 by factorial 5 x to the power 5 minus dot dot and so on, where n being a real number. So here we are not imposing being a real number, any kind of restriction, whether n is an integer or non-integer and so on. So n is any real number, right. So now we will look at the possibilities when n is an even, when n is an odd, because if it is a real number it can be even or odd, whatever. So if n is odd, if n is even, so consequently if n is even, the series y1 y1 terminates with xn, whereas y2 does not terminate, We can see that clearly, and when n is odd, then y2 terminates with xn or x to the power n, whereas y1 does not terminate, right. Thus, when n is even, y1 is a polynomial of degree n. Let us go to the next page, of degree n, and when n is odd, then y2 is a polynomial of degree n. Right. Hence, when n is a non-negative integer, when n is a non-negative integer, either y1 or y2 is a polynomial of degree n. Right. And the expression for the polynomial will come out very easily if we find out the series solution. So, the expression for the polynomial comes out easily if we find the series solution in descending powers of x, by substituting x equals to 1 by z. So, basically what we are saying, we will have z to the power 4 minus of z square, d square y by dz square minus plus 2z cube dy dz plus n into n plus 1 into y equals to 0. So, here we have z equals to 0 as the singularity, z equals to 0 is the singularity, and if we solve by Frobenius method around the point z equals to 0, then by Frobenius method we will obtain the solution as y1 is equals to c0 x to the power n 1 minus n minus 1 by 2n minus 1 x to the power minus of 2 plus n into n minus 1 n minus 2 n minus 3 divided by 2 into 4 2n minus 1 2n minus 3 x to the power minus of 4 and so on, and y2x will be c0 x to the power minus of n plus 1 1 plus n plus 1 n plus 2 divided by 1 into 2 into 2n plus 3 x to the power minus of 2 n plus 1 n plus 2 n plus 3 n plus 4 divided by 2 into 4 2n plus 3 2n plus 5 x to the power minus of 4 and so on. So, hence the general solution is y is equals to a y1 plus b y2, and putting c0 equals to 1, So, the expression for y1 shows that it will terminate. So, the expression for y1 the expression for y1 shows that it will terminate or be a polynomial when n is a positive integer. When n is a positive integer and the series y2 will not be a polynomial, right. So, similarly, we can write this for convenience, we can write C0 equals to 2n factorial by 2 to the power n factorial, and this is actually 1 into 3 into 5 dot dot up to 2n minus 1 divided by factorial n, and the polynomial solution can be written as we'll have 1 into 3 into 5 dotted up to 2n minus 1 by factorial n into x to the power n minus n into n minus 1 divided by 2 into 2n minus 1 into x to the power n minus 2 plus n into n minus 1 n minus 2 dotted up to n minus 3 divided by 2 into 4 into 2n minus 1 2n minus 3. So, here this is just n minus 3, there is no dot dot dot, x to the power n minus 4 minus, and this keeps on going. So, and if n is an odd integer, if n be an odd integer, so we have looked at if n is an even integer, if n be an odd integer, then we will have odd integer, then the series terminates, with the term involving x, and if n is an even integer, then it terminates with a constant, and this is denoted by Pnx. This series is denoted by Pnx and is called Legendre polynomial of degree n. Thus, what do we have? We have Pnx equals to 2n factorial by 2 to the power n factorial n whole square x to the power n minus of n minus 1 by 2n minus 1 x to the power n minus 2 plus n into n minus 1 n minus 2 n minus 3 x to the power 4 divided by 2 into 4 into 2n minus 1 2n minus 3 plus minus dot 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 and so on. So, basically this is our Legendre polynomial Pnx, right. And if we put P0 equals to, if we put n equals to 0, then our P0x will be, if I put n equals to 0, then P0x will be simply 1. If I put n equals to 1, then our P1x will be x and P11 will be simply 1. Similarly, if I put n equals to 2, then our P2x will be 1 by 2 3x square minus 1 and P21 will be also 1 and so on. So, basically we can see that. So, we can write down P3x also, and P3x will be 1 by 2 5 x cube minus 3x, and P3 1 will also be 1, and so on. So, we can calculate all these polynomials P4, P5, P6. So, as you can see, they are all ended up being a polynomial of degree n. So, if you are talking about P and x. So, we can easily verify that, and also we can easily verify that x to the power 0 is equals to P0x, then x equals to P1x. So, we can write x square as 1 by 3 P2x plus P0x, right, combination of P2 and P0. X square can be written as, then x cube can be written as 1 by 5 2 P3x plus 3 P1x, then x to the power 4 can be written as 1 by 35 8 P4x plus 20 P2x plus 7 P0x, and so on. So, these are some of the examples of how you can write down these x0, x square, x cube. So, all these powers of x can be written as a linear combination of legendary polynomials. So, P1, P2, P3 up to whatever order you are talking about. So, here since you have x square, you will have P2x, we have x cube, then P3x, x4, P4x. So, depending upon x to the power n, we can be able to write as a combination of P and x, Pn minus 1x, and so on, right. So, then in the series y2, which is not a polynomial, we put C0 equals to factorial n by 1, 3, 5, 5 up to 2n plus 1. So, then it becomes, what does it become? Factorial n. So, whatever we get after multiplication, 1, 3, 5 up to 2n plus 1, and then we have some expression, whatever was that for y2x, right. So, this is usually denoted by q and x, denoted by q and x. So, even when n is not an integer, we shall denote these expressions by P and x, and q and x. The factorial n will be replaced by gamma n plus 1, and thus the general solution is y is equals to a p n x plus b q n x, where a and b are constants, right. And we call this p n x and q n x as legendary functions. So, legendary polynomial, then legendary functions. So, we call p n x, we call p n x and q n x as legendary functions of first kind and second kind respectively, of first kind and second kind respectively. respectively of non-negative integral of non-negative integral order n, integer of order n. Now, there is a small derivation, it is called as Rodriguez formula. I try to derive it in a very short manner. So, let us say we have v is equals to x square minus 1 to the power n. So, then I have dv dx equals to 2nx x square minus 1 to the power n minus 1. Similarly, I can calculate d square v by d square v by dx square and so on. So, we will see that similarly you can calculate d square v by dx square. So, we see that 1 minus x square d square v by dx square plus 2 into n minus 1 x dv dx plus 2 nv equals to 0. And now from Leibniz theorem, I think you already know this, from Leibniz rule of this differentiation you can do the nth order derivative here. So, if I do the nth order derivative, so then in that case by Leibniz rule this will reduce to 1 minus x square dn plus 2 by dx n plus 2 of v plus n minus of 2x dn plus 1 of v dx n plus 1 minus of n minus 1 dnv by dxn plus 2 into n minus 1 x dn plus 1 v by dxn plus 1 plus 2 into n minus 1 dnv by dxn plus 2n dnv by dxn equals to 0. So, from here we will get 1 minus x square dn plus 2 v by dxn plus 2 minus of 2x dn plus 1 v by dxn plus 1 plus n into n plus 1 dnv by dxn. So, if I put dnv, so if I put dnv by dxn equals to vn, which is basically ddn of dxn x square minus 1 to the power n, then this is nothing but our usual 1 minus x square vn double dash minus of 2x vn dash plus n into n plus 1 vn equals to 0. So, that sort of looks like our Legendre differential equation, right. So, putting this we see that, so putting this we see that Vn satisfies Legendre differential equation, Legendre differential equation of order n or of our degree n. So, we when expanded, so when expanded Vn will be a polynomial, in descending powers of x, obviously descending powers of x, but in that form Pnx is the only solution, hence if Pnx is the only solution, hence our Pnx must be equals to some c into dn dxn. That means, if Vnx is a solution and Pnx is a solution, that but we are saying that Pnx is the only solution. So, that means Vnx will be Pnx will be some constant time Vnx. So, that if Vnx is a solution, Pnx is also a solution. So, having a constant will not disturb the solution part, that whether Pn and Vn they are both solution or not. So, I am saying Pnx into the constant equals to constant into Vnx, which is basically dn by dxn of x square minus 1 to the power n, where c is a constant, right. So, our P n x must be then this C n, and to determine the constant C, to determine the constant C, we equate the highest powers of x on both sides. So, we know the expression of P n x, and we know on both sides, and we know what will be from here after doing the derivative. So, if we equate, it will be 2n factorial divided by 2 to the power n factorial whole square. Highest, we are equating the coefficients of highest powers of x. So, this equals to into x to the power n, and from here I have c dn by dxn of x to the power 2n. So, from here I will get c into 2n, then 2n minus 1 dot dot and so on. I will get 2n minus of n minus of 1 x to the power n. So, basically this will be c into 2n factorial by n factorial x to the power n, and therefore, x to the power n will get cancelled, and I will get c equals to 1 2n factorial will also get cancelled. So, I think it will be 1 by 2 to the power n factorial, right, and hence our P n x, will become 1 by 2 to the power n factorial dn by dxn x square minus 1. So, this is another form of Legendre polynomial or Legendre function that is given by 1 by 2 to the power n factorial n dn by dxn x square minus 1 to the power n, and this is called as Rodriguez formula, the very celebrated formula for Legendre polynomial. So, you can remember the earlier form that we wrote down for P n x, or this is the widely accepted form for our Legendre polynomial, right. And from the calculation point of view, we can verify it will actually be similar to those P1x, P0x and P1x that we determined. I mean, P0x we can see right away, right. So, if you put n equals to 0, then it becomes constant, or 1 basically. If we have n equals to 1, then it will be 1 by 2, and here it will be 1. So, 2x and 2 will get cancelled. So, you will get P1x equals to 1. So, whatever derivations that you will get from here, it will be same as the one which we derived earlier. But this is a very widely accepted formula, and people use this expression, that is the Rodriguez formula, to do any type of calculation associated with the Legendre polynomial or Legendre differential equation, right. So, I wrote down, I mean I did the derivation, but in a very short manner. So, I wrote down important formulas, but if you are really interested in the whole derivation, you should look into the textbooks that I have recommended, or you can find them in any general textbook on differential equations or special functions especially. So, these are the two special functions that I wanted to talk to you about, the Bessel's function and the Legendre polynomial. So, I have concluded these two topics, and then from the next class we will start with Sturm-Liouville problem, and finally we will also look into Laplace transform and the solution of ordinary differential equation using Laplace transform. So, I will stop here today, and we will continue our discussion on Sturm-Liouville problem in the next class. So, thank you for your attention.